complex adaptive matter.
Thank you. Great. So ICAM is the Institute for Complex Adaptive Matter, and then I2CAM is the International Institute for Complex Adaptive Matter. The only practical distinction is that this is the name of our NSF grant, which is the most significant source of funding for an international materials institute, U.S. National Science Foundation. My co-director is David Hines, who many of you know as a distinguished theoretical physicist who worked with more Nobel laureates actually than anyone in history, I guess, in terms of papers. And you Oppenheimer and Einstein and so on. He's a terrific resource and a very energetic octogenarian. Some history before I tell you a little bit more about what we do. ICAM was founded informally in 1999. Was formally named a multi-campus research unit of the University of California in 2002, and a number of other campuses around the country joined on at the same time. At that time, it was basically housed in Los Alamos National Lab, and we moved the headquarters to Davis in 2006. And we're sponsored by the National Science Foundation and our branches in a way that I'll explain to you later on. But what about the central mission of our organization? We see our central mission as the search for the organizing principles of emergence in matter. If you're wondering what emergence is, I'll give you a hand-wavy description in just a second. That search for organizing principles, we really believe strongly, has to be experimentally driven. We're not like the string theorists who think that you can come up with a beautiful theory to explain the universe. We really think you have to come up with the description at the appropriate length and time scales from experimental data. And here's just an example to give you an idea if the concept of emergence is fuzzy. Emergent phenomena are basically things that owe their existence to interactions between well-understood subunits. But you wouldn't easily predict the phenomena on the basis of a knowledge of those subunits alone. So for example, how can a collection of molecules think about what molecules are? Consciousness is clearly an emergent phenomenon. We're not doing consciousness yet, but maybe, I don't know. We define complex adaptive matter as materials which exhibit emergent phenomena. For example, the superconductivity recently discovered in the iron arsenic compounds, amyloid assemblies of proteins, a lot of interesting phenomena in liquid crystals, and of course there's still a lot of emergent phenomena in these organic photovoltaic devices and other photovoltaic devices that we're hearing about here at this meeting. We're really an organization that's grown all around the world. We have over 60 branches around the world. This is just some history of branches. We've deleted a few along the way, partly due to economics or changing motivation, but we've even added 9, I think it is, in this last year. And this is where the branches are. You probably can't read the fine print, but I tried to mark with arrows all of the branches where we know that there are large energy programs, as well as policy and social programs. This seemed appropriate to the kind of panel discussion we had yesterday about how to move alternative energy forward into the future. So that would include Davis, where we're headquartered, but Stanford, the Santa Fe Institute, MIT, Boulder, Michigan, the consortium in Zhejiang, China, which just had a meeting earlier, just last month, and of course Queensland and Cambridge. There's more on here, but I just put these up as an example of the global outreach of ICAM. Our North American branches, our Asian, South American, we actually have one more South American branch to add here, and our lone Australian branch, and our European branches, and our one Middle Eastern branch right here. And we also have, with a lot of help here coming from our co-chair of this program, Ivan Smolyak, partner institutions where we're trying to reach out to underrepresented groups in the United States to bring them into the science of emergent matter. So why a network, which is what ICAM is? Why a network to do this? That's basically what we do. We link people up all over the world to do science in these areas. Well, we strongly believe that the key problems, such as novel photovoltaics or getting to higher temperature superconductors, protein aggregation problems in disease or for useful purposes, that those are too big for one discipline, institution, or country. And we would call ourselves emergent because the participants dictate and decide the science directions, and each year brings fresh ideas. So you can apply for workshops, for fellowships, for exchange awards, all of which can help to foster these studies of emergent matter. And that's from the ground up. We just try to set up an administrative structure where you can do the work and make things happen. And our main thrusts are in soft matter, quantum matter, and biological matter. with novel materials for energy being something that we're trying to get into. But we want to do that in a way that makes sense, that we're not just one more group trying to glom onto what is clearly going to be a growth area of science. We want to help and find a value-added way to contribute in this area. But this gives you an idea of some of the topics that we've been into. Liquid crystals, oops, colloidal matter. Oops, what happened there? That's weird. I didn't do anything. No? Let's see. No, that's really weird. It shows up here, but it's not showing up there. No signals detected. Please connect video. That's weird. It was all funny. Yeah, yeah. I'll kick my new MacBook Pro. That's it. Yeah, there we go. Let's see. I can't even get the. Oh, there it is. Let me see if I can get it to reboot here. That's very strange. It was fine. I didn't touch anything. Let's see. No signal. Well, should I reconnect it? Yeah, this is emergent phenomenon. I wouldn't have predicted this. Yeah. Yeah, that's what I'm doing. Here we go. Let's see if this does something. Well, it makes my laptop flash, which is interesting. This is very strange. Yeah, it's just, you see it's showing it there, but it's not, yeah, let's see if there wasn't some problem. Yeah, oh, no, that's up. Okay, now let's try changing back to the laptop. That's very strange. Okay. Just changing back to the music. That's off. Maybe we'll just, oh, that's on. Okay. Now let's change it to the laptop. Huh? Yeah. Okay. Great. Yeah, if we can't get it to work, we'll just do that. That's that seems to do something, yeah. There you go. Now let's, we're not doing the source yet. Oh, yeah, it's showing the computer on the other side. 3, 2, 1. Ah, gosh. This is why, you see, I told you we need experimental science. Okay, let's see here. Sorry, I have to... Oh, so I'm giving you a sneak preview of what I was talking about there. All right, so the main ICAM activities are that we have of the order of 10 NSF-sponsored exchange awards, which are for graduate students or postdocs to work between two mentors, between ICAM branches, basically one in the mostly between the United States and other countries, with one in the United States and one abroad. And the average of those is probably 10 to 15K, some are longer because they go up to 12 months. We have 5 to 7 annual branch fund sponsored fellowships each year for postdoctoral research between any ICAM branches at all, and for sabbatical research for senior scientists. 45 to 60 travel awards for junior scientists each year. In all of these, except for the fellowships, up to 5 to 10% of them are for non-ICAM branches. We orient ourselves towards the branches, but that's not what we limit ourselves to. We have 10 to 12 exploratory workshops every year, and we have 4 different schools each year, continuing one at Cargès in France, a continuing one in Rio de Janeiro, a continuing one in Bangalore at the Nehru Center for Advanced Scientific Research, and of course ICAM. And we have some outreach activities I'll tell you a little bit more about in a minute. And of course, because we're a network distributed internationally, our web pages are quite critical. So what's an example of some of our successes? Oh, sorry. We try to be nimble, we try to be adaptive, and as in our name, the fellowships we decide once per year. The workshops we decide every quarter. Exchange and travel awards are open anytime, but it's helpful if you give us 2 months notice before a trip rather than the day before. All applications are online at our website, i2cam.org. And here's an example of a junior fellowship. So we had a guy you may know, Ivan Smoljak, who wanted to work with another guy you may not know, Tom Mason. Ivan, of course, does beautiful work on liquid crystals and optics with liquid crystals, and Tom has worked on the chemistry and physics of colloidal systems. And they came up with an idea for a project together, but the problem is to get them to interact, of course, you need a boson, and that boson is Clayton LaPointe, who's done really well, actually. In fact, their collaboration led to a paper in Science just last year, which has to do with putting in shaped colloids, triangular-shaped colloids, into liquid crystals. And when the colloids interact, you're able to get interesting and beautiful tunable optical properties to the liquid crystal colloid assembly. And this is an example of the kinds of interactions we would love to foster. Another one which was quite successful was an exchange award between the groups at the University of Tokyo, Yuchida's group at the University of Tokyo, and Seamus Davis's group at Cornell. There's a lot of details here. I won't go into all the details because that's not really what's interesting. It did get on the cover of Science, but what was the experiment? Well, the simplistic description is that Kazuhiro grew his samples in Tokyo and took some of the best samples of the bismuth strontium copper oxide superconductor over to Cornell to measure with the ultra-low temperature scanning tunneling microscope that Seamus has in his lab. And they found something pretty amazing, that when you look at the surface at low temperatures, if you look in topography mode, you see that there's a surface with defect structures on it, like this right here. But if you look at it in a suitable way at the electronic density of states, you find that there's an inhomogeneous, intrinsically inhomogeneous electronic density of states, or electronic density on the surface of these bismuth strontium copper oxide superconductors. So what's interesting is that the disorder, which is a kind of bond disorder in the electrons, does not correlate with the structural disorder that you can observe corresponding to the defect structures. And so the idea of this intrinsically inhomogeneous electronic state is a fascinating idea, and at least ICAM was able to help contribute to the discovery of this phenomenon. Another thing that was using one of our travel awards, let's see, Avinash Kane from UC Davis and Livermore, working with Olga Bakagin, was able to go over and construct a rig and a synchrotron in Germany where they could do ultra-fast studies of protein folding. And this was a very nice paper that advanced the measurement of protein folding that appeared in PNAS a couple of years ago. We've had exploratory workshops of all different kinds. For example, one on local probes in strongly correlated electronic materials held in Dresden a few years back. Of course, Yvonne has been running these ICAM schools. These are pictures from the school in China last summer where they moved between 3 different cities. Here in Australia, they're limiting themselves to just 2 cities, but that's still pretty exciting. And next year, they want to move between, I guess, Montevideo and Buenos Aires in South America. As Yvonne said in his report on this, the main goal is to combine advanced graduate level education with learning about diverse cultures around the world. The students can vouch for whether this is effective or not. I think it is, and I'm really excited about it. We had a school on biological physics in Rio de Janeiro that was held a few years ago through the Fabergé School. This is Eric Watkins from Davis. These were some students at Cecilia Clemente's lecture. This was a tutorial about using nuclear magnetic resonance for doing protein determination. And here's, just to give you an idea, here's some recent and upcoming workshops to show the span of science that we cover. We had one on memristors and resistive memories in Davis in January, one of the first ones I'm aware of on this exciting and developing subject, which may be a new way to do computers. Nuclear core complexes this month in Santa Fe, quantum simulation and metrology next month in Michigan. Dynamics, school on dynamics and soft condensed matter in Cargez next month, and a workshop on water and biological systems in Chicago in September. So if this interests you, you might wonder, as Queensland wondered and did do, how do you become a branch? Well, each branch agrees to contribute 10,000 US dollars in direct support to ICAM central funds or via in-kind support. For example, support for ongoing schools. We tend to prefer this because we can use it for more things that way. With holding an additional $10,000 at home to do activities for building up your branch at home. Only the branches can participate in fellowships, and branches receive preference for workshop participation, organization, travel, and exchange awards. They get the vast majority of those. But it's not an exclusive club. In 07-08 of 266 senior participants, 40% of them came from non-ICAM branches. 266 participants out of 668 came from non-ICAM branches. That was 2 years ago, where we did a careful counting of that. It's also much bigger than the U.S. Only 140 of those participants were U.S. citizens or permanent residents. So it's very much international. Just to tell you about our funding numbers, we get now an average of $1.05 million a year from the NSF through our International Materials Institute grant. That was increased from our first 5-year award, which was $700,000 per year. So we're quite happy with that increase. It allows us to accommodate more branches, more activities. From our branch cost contributions in terms of what actually comes into Davis, that's somewhere in the ballpark of $550,000 a year. And various foundations have contributed for outreach activities and engagement activities, about $40,000 a year. So we're about $1.6 million a year right now. And on the participants, just so you know, this is from our just recent NSF report. We had on the order of 1,000 people participate in this last year. The faculty participation has a center of gravity in physics, but there's a lot of people from other disciplines who contribute. This also shows you how we're doing on diversity, which is something the NSF is very interested in. Around 70 postdocs, several hundred students, and even about 30 undergraduates participated in our activities. There have been a high level of publications from our grant since its inception in 2004, about 93 publications, including high-impact journals. And so far as I've been able to count, we have about 450 citations so far from these papers. And when you count overall ICAM publications, about 150 of them associated with ICAM activities over the years. And this is just showing you a little bit about our exchange awards, which then fills in, and it just gives you the idea that we're creating exchange spaghetti around the world, trying to wrap the world in ICAM spaghetti, and also similarly with our travel awards, that fills in more quickly. We've inspired some grants around the world. For example, Henri Louel in France was inspired by ICAM to write for a Marie Curie Action Award from the EU, and got around $700,000 a year for 4 years for activities on strongly correlated electron materials there. There's an ESF subnet on theories of emergent phenomena in it's called Intel Biomat. It's an ESF subnet on theories of emergent phenomena and correlated electrons and biological systems and nanosystems. Ross McKinsey got this discovery grant here, which is actually paying for the Queensland membership in ICAM. And the PSI-K network for electronic structure based in Europe instituted a cost share fund similar to ours. So we've inspired some other activities around the world. Let's see, the emergent universe, we have a number of public engagement activities. I'll just show you the emergent universe real quickly because we're very proud of that, and we could add a wing to that on alternative energy materials. We'd really be delighted. We have some other things. We have some short videos of scientists explaining their work. We have lab modules for high school teachers on superconductivity, magnetism, and I guess perhaps liquid crystals. I'm not sure where that is. We have hosted the Condensed Matter Journal Club of Chandravarma, although that's shifting to Riverside, UC Riverside now. The Music of the Quantum is a beautiful website that emerged from a conference we had in New York City a few years back, and we actually commissioned music on quantum criticality, which you can listen to on the website. And then we have an online encyclopedia of emergence in matter called ICAMopedia. But the Emergent Universe Museum is not like anything you will find out there. Let me see if this works. Okay, let's see. So here is the homepage of the Emergent Universe Museum. It's oriented towards people who are college students, high school students, young people who are used to playing around with websites. Older people are not, and are not used to wiggling things around to find what's going on the website. But it's an online science museum. It has two wings to it right now, and little things pop up as you move around. So, for example, there's bees, but I can click, there's the fibril connection, which will tell you about renegade proteins in Alzheimer's disease, for example. You can zoom in on the brain to search for a cure to Alzheimer's disease. This takes a little bit of time, so I may not download it, but you get the idea that this is a game on making the fibril connection. This is artwork and dance and movies on understanding the human face of Alzheimer's disease. There's also one on the general concepts of emergence, and it's a general, we're developing a wing on superconductivity right now. Oh, here we go. There, are amyloid fibrils toxic? What are these? What's the nanoscale? These things pop up. Got amyloid? Let's see. Anyway, you get the idea. And this is showing you spiderweb because amyloid is a key constituent of spiderweb. That's why the spiderweb shows up on that picture right there. So this has been one of the things that we're very proud of, and we'd like to add new wings to it if possible. Okay. For more information, you can go to our website, or you can email me. And also, I just want to leave you with this message. How can I2CAM contribute in a value-added way to these energy questions that we're focusing on here? And we want to hear from you. Okay, and I'll stop there and take any questions. It's bumping this, that's what happens. It's bumping this thing. Okay.
Do we have any questions?
First question is, where's lunch, right? Actually, let me ask, since we have a number of people from the Boulder group, how many of you have actually participated in travel award or exchange awards? If you could raise your hands. Okay, okay. And how many of you junior people might be interested in travel awards or exchange awards? Okay, well, a few. Okay, good. Okay, so keep us in mind. Thank you.
Okay, we will return here at 1:30 sharp, if not soon.